Cool. Well, might work here. Too close? No, that's cool. Okay. So last time we got into 3-4, we haven't finished 3-4 for sure. We have not finished that thing. Any questions on the homework? Yeah.
For 3.2 number 6, I don't understand what it's asking.
Okay. Let's see. Yeah, let's see. This is a very strange way of putting things. Oh, all right. So, for example, number 6, every single one of those parts of number 6 are based on, so if I put up here x plus 2 to the 4th minus 16, what shifts has this thing undertaken? How do you have to shift it? You have to move it up and down, left and right. Yeah, this would be left 2, down 16, 11. So now take those out. So very often it's funny, you can identify the shifts. Now take them out. What are you left with? If you took them out, what function are you left with? Beautiful. So that's your base function is x to the 4th. So draw an x to the 4th and then just move it around. Yeah, cool. So whenever you draw that, the base function, so x to the 4th, it looks a lot like x squared. It's just, of course, goes up a lot faster, right? It ends up being skinnier. So like 2 would go to 16. Holy crap! So it goes up pretty damn fast. It's really skinny. So now just move those points around. And remember that 2 goes to 16 because that's interesting. They put that there. That's going to bring that point down to 0. Right? That kind of thing happens. So when you see that transform, that shift the base functions, and that's what they mean. For me, doing a dotted line, what it would look like with no movement, and then move it around. Cool. Cool. Yeah. And the same section? 3-2? 15. The one that says this here? Plus. Oh, okay. So, what would this would be a nice little review. What would the end behavior be for this? Yeah, it's parabolic, right? So it's squared. So the end behavior is going to be up and up, right? It's a positive coefficient, so it's not going to be down. The nice thing about having it written like this is it's already factored, so what do you know already? The intercepts. Yeah, so what are the x-intercepts? Yeah, be more specific.
1, 0, and 2, 0. Negative 2, 0.
Negative 2, 0. I like it. Cool. And they say, make sure your graph show all intercepts and exhibits the proper end behavior. We can go one step further. I think in 3-2, yeah. We know at this point the shortcut for finding the vertex. This happens to be a parabola, so you could find that vertex if you wanted to. They don't really say to, so. But how would I find the vertex? And actually, I can do it a little bit different way. If I start to graph this thing, I know it goes through 1, 0. I know it goes through negative 2, 0. Where must the vertex be? Halfway between them, which is where? I like it. So 1 in, and then half in. It's got to be a negative 1/2 somewhere. So if you plug a negative 1/2 in, you'll actually see where the lowest point on the graph is. And that's actually just about the most important point for a quadratic, is that lowest point, right, or the highest point, the vertex. But that's really what they mean. They want you to sketch a rough graph of it, so it doesn't even have to be that perfect. You don't even have to find the vertex, but it's got to have the right end behavior, and it's got to have the intercepts, right? Of course, I left something out. To be a little more specific, what's the y-intercept? How do you find the y-intercept? You make... Yeah, and this is one of the things I really don't totally understand. I don't care what level of math you're in, to find the w-intercept, you make all your other letters 0. So thankfully, we don't have 26 variables in our equations yet, right? But we only have 2. So awesome. To find the y-intercept, you make x0. To find the x-intercept, you make y0. Always, right? It doesn't change. So how do I find the y-intercept? Make x0. So I get -2. So if I make my scale correct here, yeah, there you go, Jeff. You did it right. And be careful when you're doing these graphs. Dear God, I do not want to see that. And then there's nothing. Right? A little bit better is if you mark this, but you have to show me the scale on both axes. You with me? And if you are anywhere near as messy with stuff as I am, get yourself some graph paper. Right? I need to see some detail. Doesn't have to be perfect. Right? I didn't find the exact vertex, but it doesn't matter. They just want a rough sketch. Right? But it has to show me some scale. It has to show me where your points are. I should be able to see those things. This, I don't know what the hell it is. Okay. Any other questions from homework? Is that good enough? Who asked that question? Is that cool?
Yeah.
Okay. So the other ones are not necessarily going to be quadratic. But you do this, you plot the intercepts, you make sure the end behavior is correct, and then you fill it in. Cool. Any other questions from homework? Okay, I continue to be an optimistic fool. So this means that homework is going great. This is true. Are you guys going to the Math Study Center? I know you're not coming to see me, which makes me feel really bad. I don't know if I have made myself seem inaccessible or something. You can always come see me for help. Grading some of the homework, I can see some of you guys need some help. So this is the point where you got to really start stepping up and taking advantage of the resources that are free, like me or the Math Study Center or the upstairs tutoring center. There's all kinds of help here. It's crazy. So you're not totally on your own. So if there's no other questions, maybe this will spur some questions. We're going to have a quiz on sections, I think, 2-7, and I'll go up to 3-3 Monday. So 2-7 was the inverses one that was left off of the last test. So it's on this new stuff. Up through 3-3, that goes up through synthetic division. But that does not include section 3-4, which is the one we still need to finish. So I try never to make a quiz over something that I'm still lecturing on in the class before that. Does that make sense? Okay. So I think last time we definitely know the process for synthetic division, or at least we've seen it. I always got this class before me last semester. You guys see the? Is there an eraser in this classroom? Okay. Well, it really sucks a lot. There's no erasers at all anymore. So let me get to a point where I'm going to let you guys work on a worksheet. And I will just, attempt to work with what I got. And then find an eraser. One of the high-tech erasers we have. So real quick, I want to make sure everybody remembers how to do synthetic division. So do this for me here. So synthetically divide that. Don't do this with long division. That might give me enough time to go find an eraser. Here. Just make sure everybody's got this set up right, because there's a couple of things. What goes in the penalty box? 2. And what's the thing you have to be careful about?
0.
There's no x cubes. Good, so it's got to be 3, 0.
-2.
Sweet. And then once you see the process, I mean, it kicks long division's ass, but long division still exists because this only works for what kind of things? It's remarkably specific.
Linear.
Not just linear even,
Denominators.
with the 1 out front. This synthetic division is so easy because it has so many ingoing requirements. It can only be linear, it can only have a 1 coefficient. You with me? So of course it's going to expect to be kind of clean. This is kind of cool though. How does this work? 3 down. 6. 6. 12. 10. 20. 5. Good. Alright, that didn't get too bad. Good. We'll never make one up like that out of nowhere. I'm worried the last number is going to be like 18 million something. So, what's this then? What's this equal? Now something that happened here that's really kind of cool that's going to feed into today's discussion. Now let me just kind of analyze this a little bit further. So is 2 a factor? Is it a 0 of this? No. Right, and that's the same thing as saying x minus 2 is not a factor of this. Right, those two things mean the same thing. But notice something interesting. So what we got here is that this 3x4 minus 2x squared plus 5x minus 11, that equals, how do I sort of factor it? Don't really factor it because it's got this piece in it, but it would equal x minus 2 times this. Blah, 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 blah. All right, now go with me. So this started off to be just an exercise in making sure that everybody can synthetically divide. And I wish I could claim credit that I made it do something on purpose, but I didn't. It just happened to do it, so it kicks ass. I'm going to use it right now. So 2 is definitely not a 0, right? But for everything greater than 2, now go with me. This has immediate implication with something later in the section. For everything bigger than 2, that's going to be positive, right? And every single term in here is positive. So if I plug in any value of x, could there be any value of x that would make this become 0 that's bigger than 2? Is there anything above 2 that could possibly make this 0?
No.
Hell no. What kind of x could maybe make this 0? What kind of value of x could maybe make this 0? Negative, because this is all alternating stuff. You with me? Not alternating, what is this? They're all positive. Think about the next step of this. I'd have to have a negative value to make some of them cancel out with other things. If I plug in here specifically a number bigger than 2, that's positive, how are they going to cancel each other out to become 0? So what does this really mean? Remember what we got into the other day. We said, if I want to really break something down, I have to write all the possible factors of it from that last number, divided by the factors of the first number, right? And that list can get stupid big. So I really want to find a way to chop that list down. So the list for this one will not be all that big. Oh well, I'll survive. But imagine I had a list like plus or minus 1, 2, 4, 10, 20, 60, 120, blah, 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 blah. And then some fractions in there, 1/3 and 4/5, and who knows, right? Good God. The really cool thing about this, if I synthetically divide, and I see that all my answers are positive, that means that there's no answers above this number. This is called an upper bound for the answer. Does that make sense? It's a bound. It says there's nothing beyond 2. 2 don't even work, but there's definitely nothing beyond 2 that would ever work. So what could I do with my list? I could chop off positive 10 and positive 4, and 2 doesn't work already, right? I still have the negatives of these guys, but anything 2 or bigger, they're gone. They're out of my list. I don't have to check them. Thank God. Some of you guys might be realizing if I can't cut my list down, that means I have to just keep trying stuff until something works. And if you're not lucky, that could take a long time.
And actually, if they're all positive like that, wouldn't even 0 not work? Because then that last 25 on the end would make it 25? Or the last 39 on the end?
Yeah, exactly. 0 won't work. Exactly. But there are times, I mean, if it's like, if it's below 2, then this number here would be negative. You with me? 0 wouldn't work because it would make, well, you gotta be careful. 0 would make this, the answer would be this plus that over -2. Alright, well, I want to make sure everybody's with me. Are you guys kind of cool with it? And I love this because the theorem is difficult to understand until you really just take a second and think about it. Well, of course there are no numbers bigger than 2 that would ever make this 0. It's just always going to be positive forever after 2. But why might 1 work in a situation like this? It doesn't work here. Because all this stuff would be some positive number, right? But then 39 divided by 1 minus 2 is negative 39. So maybe all this stuff is 39, and that's minus 39. Hey, 1 makes it 0. 1 would be a 0. 1 would be a factor. You guys am I with me? So that's why I have to say anything above 2 won't work. 2 is an upper bound. So we'll see. We'll get back to that. I'm doing this a little bit earlier than I wanted to, but that's just because this happened to happen. It's awesome. Okay, let's see how this works. Sweet. All right, good. Just as good as the really expensive ones they give you normally. Okay, so the other thing we did last time was we started talking about a problem like this. Still 3-4. Yeah, 3-4 is just chock-a-block full of stuff. Okay. So somebody help me out. What's the list of possible rational roots? How do I put that together?
193.
Yeah, so the factors of the last number divided by factors of the first number. And we looked at a few examples of why that makes sense. If I have 2x minus 1 as a factor, the root's going to be 1 over 2. So those numbers out front do end up on the bottom of the answer. So that's why I divide by the factors of that. So it's going to be divided by the factors of the first one, too. So on the top would go 139. Bottom is this. That's not good enough for an answer, right? When I ask that question on the test or a quiz, that's not enough. Just take a second to figure out what those numbers are. So since it's divided by 1, you're going to get 139 back. What else do you get?
1/2, 3/2.
Yeah, exactly. You get 1/2, 3/2, 9/2. Do you guys see that? Just make all the ratios of the factors of the last dude over the factors of the first dude. Those are all the possible roots of this. So for example, since 9 is a possible 0, what root would that relate to? X minus 9, right? So x minus 9 might be a factor of this. That's how those two tie together. That's why synthetic division is a factoring tool. It helps you find the zeros, which you can then just put into a little factor like that, right? That's where it would come from. Okay, cool. I do that a lot. This is not a huge list, right? This is not a great big old list. But do this. Synthetically divide by 3/2. Take a minute and do that. I don't think we've done many fractions yet. Here's one. Alright, so it should work. Let's see. So you bring the 2 down. 3/2 times 2. 3. 8. 3/2 times 8. 12. Minus 8 is 4. 3/2 times 4. 6. Negative 8. Negative 12. Negative 6. Negative 9. Sweet. So I just want to make sure that we can see how, doing a factor, a fractional answer would still work. All right, so don't be scared of those. Notice something. Let me see. What did I say earlier about the results of this? Notice something about all of these. What does this really mean I've done so far? How have I broken this thing up? Good. X minus 3/2. Yeah, I started with a 5th, so now it's a 4th. It always goes down by a power of 1. Plus x cubed plus 4 squared minus 8x minus 6. I went in evenly, so I don't have any remainder. That's kick-ass. So that's an answer. Now, I'm not going to start making factors, doing all my factors of 6 divided by my factors of 2. That would be not smart. Because I could take out of this, what? 2, and then put it up there. That's what I was saying about when you divide by a fraction, you have to be careful. You can just pull that coefficient out of somewhere else to complete this 2. So if I put that 2 back in here, take a 2 out of everybody, this will now be 2x minus 3, x4 plus 4x cubed, 2x squared, plus 4x minus 3. And the reason that's really nice is because what does my list look like now?
1, 3.
Let's say it one more time.
1 and 3.
1 and 3. And then because the first number now is a 1, that kicks ass. So now my list becomes plus or minus 1 and 3 for the 3 at the end. And that's all I have to try out now. Let's just try those out. So try to finish it out. Try to figure out what the other roots are. So far we got the 2x minus 3 from that 3/2 root. Try to finish it out. Remember, you're going to start with this guy now. So you're going to synthetically divide this. Oops. Oh yeah, this one. So let me know, has anybody got one that works? What works?
1 negative 1.
Alright, 1, negative 3. And in fact, the funny thing is, the minute you get one that works, you can't chop it out of your list. Why not? Now 3/2 work, and it's not in my list now, just because my new thing I'm worried about has a 1 out front. I'm not going to get fractions, are you with me? But if 1 works once, it might work again, right? Or if negative 1 works, it might work again. Because I might have a factor that would be like x plus 1 squared. I might have it show up twice or 3 times, or who knows. So just because it works, don't throw it out of your list. The only time to throw it out of your list is if it doesn't work. So if you do 1, let's see, 1, 5, 5, 7, 7, 3, 3, 0, kick ass. So far we've got 2x minus 3. What does this guy do for me? X minus 1 times so next plus 3. I like it. So that's what we have so far. We'll do that to you right now. Let's see. So now my list is basically the same, right? I have plus or minus 3 over plus or minus 1 is the same. It's plus or minus 1 and 3. So somebody told me that. What do you say? Negative 3.
Yeah.
So if we do that into this new guy here, 1, 5, 7, 3. See, 1, multiply, add, multiply, add, multiply, add. Kick ass. So now what do I have? This is going to be 2x minus 3, x minus 1, and what's this guy? X plus 3. He was an x cubed, so now he's a x squared. And what's really nice about the last dude, you need synthetic. Hopefully you don't, because that can factor nicely, right? So you get 2x minus 3, x minus 1, x plus 3, and how does this factor? I like it, x plus 1, so you just say x plus 1 squared. So if anybody got negative 1 to work, it would have worked again, because it shows up twice. So we've done two things here at once. We've factored this dude, but now we've also answered the question. If the question was that, if it was where does this thing equal 0, we've got the answers there too. I could just collect them along the way. Right? X equals 1 and x equals negative 3, all the stuff that actually went in. Okay, cool. How do you feel about that? Sorry, yeah.
In the very beginning, when we divided, when we did the 3 halves, would we have to go through the list of like all the other factors so we could find that one answer that would work?
Yeah, exactly. I see the idea. So that's why the very next thing I'm talking about is what do we have that will help us reduce that list? I talked a little bit about the bounds thing, so I want to make that a little more formal. And there's one other thing that sometimes helps and sometimes doesn't do anything. So it depends. Yeah. Okay. So let me see. So let me first talk about the bounds thing I was talking about earlier. Let me complete that idea a little bit. Has everybody got this here? Okay, I'll leave that open. I'll need you. We don't. All right. So the idea with the bounds, the one thing we already talked about was this. If you synthetically divide, this is on page 257. How do I summarize this? If you synthetically divide by b, and your answers are all non-negative. If you get zeros anywhere, you could actually look at them as negative or positive, because that's what 0 is. It's both, right? You with me? This bounds theorem relies on you knowing, are they all positive, or the other one's going to be, are they all alternating? If you get a 0 anywhere, it's like, what the hell does that do? Well, it's positive or negative, whichever one's going to make it fit. So if you synthetically divide by some number b, and your results are all non-negative. Doesn't mean the same thing as positive, because it includes 0. Synthetically divided by b and your results are all non-negative. Then b is an upper bound. For all the roots. So if you have anything in your list that's bigger than b, that are possible roots, you can just cut them out. You don't have to worry about them anymore. That kicks ass. Now, I've already discussed why this works, and hopefully that made sense. I'm not going to go through some big proof of this. It's not difficult to figure out why this kind of leads to this conclusion. Okay. So the other way, if you synthetically divide by b, and this is on page 257, by the way. They say it a little more formal language. You don't have to write this down if you want to. If you synthetically divide by b and your results are all alternating in sign. So it's positive, negative, positive, negative. Or it might be positive, 0, positive, negative, 0. Right? The zeros in the middle would just be positive or negative. If they alternate in sign, then what do you think is true to make this nice and symmetric, this theorem? Then in that case, b would be a lower bound. I love it. There's no negatives below that would work. Or no number below b. B might be positive. Results are in the sign. Then b is a lower bound. For all the roots. So one thing that this immediately helps with, even if a function, if a polynomial I'm looking at doesn't have any nice zeros. Like all of its zeros are 1.097246 or square root of 7 plus 2 divided by 3. I'm never going to get that. Unless I use quadratic formula, I'm never going to get that by factoring this thing, right? I'm not going to get that. But one thing I can do, I'll give you an example here. It's kind of a crappy example. Yeah, that'll work. Okay. Semi-crappy, but that's all right. Okay. So not even worried about the candidates for possible roots. If you synthetically divide by 2, let's see what you get. You guys have started already. Added and multiply correctly. So how do I interpret what I just did? What does that mean? I like it. Good. I love it. That was an open-ended question, so you're right. That means that 2 is not a 0 of this. Was 2 even a candidate for being a 0? No. So it's like, oh, good job, Jeff. But what do I see from this?
It's upper bound.
It's an upper bound. So, for example, 3 couldn't possibly be an answer here, right?
So it's only 1?
No, it's not only 1. It could be negative. So all I know right now is that the answers have to be from negative infinity up to 2. There's no numbers beyond 2 that could possibly make this work. So if you go on the other side, if you synthetically divide by negative 3, now that makes a little more sense because it could possibly work. So you get 3, negative 9, negative 5, 15, 8, negative 24, negative 26, and then who knows? What is that, 78? Sounds right. So what do you notice about those numbers? They alternate. It's positive, negative, positive, negative, positive. Which means that negative 3 would be a lower bound. So that means that my result, my values of x that will make this work, all the real ones, have to be between negative 3 and 2. And of course I don't include negative 3 and 2 because I already know that neither one of them works. Right? I got remainders on both of them. So if you were to graph this in your graphing calculator to try to see the answers, what could you be smart about now? Considering this.
Shrink your window.
Yeah, exactly. Make your x-axis scale from negative 3 to 2. And you're guaranteed to see all of them in there if there are any. Now why do I say if there are any that you can see in the calculator? What kind of roots would you not see in the calculator? This is getting a little ahead of us. But just
Roots unless you set it to. Imaginary roots unless you set
I love it, right? Complex roots. You can't see complex roots on a real graph. Cool. And there could be nothing but complex roots here. Who knows? Okay. And I don't know how much you guys understand about complex roots. We're going to get into complex numbers in the next section. But just a real quick example, what's the end behavior of this dude? Yeah, like that. Parabolic, I love it. And he might have some turns and twists. And if he's too far up in the air, he could do this kind of thing. Are there any real roots? No, hell no. There you go. That's why they could be all complex. Who knows? But I know if there are any real roots, they have to be between negative 3 and 2. Cool. Okay. Okay. All right, so let's do this. Let me give you guys this. So just to give you guys a major hint about the next test, I love putting a problem pretty much exactly like this on the test. So that's even more than a hint. That's just a direct, hey, this is a good problem to look at. Oh, and of course I haven't talked about it. Let's talk about this here. I always talk about that first, and now I'm going to talk about it second. So we know how to do bounds, and that's what part C is all about. It's going to get the bounds, and you can kind of see from the language, divide by 8, divide by negative 8, what does this mean? That's going to be the bounds. Here's the one I keep saying is sometimes useful and sometimes isn't. And it's comes from Descartes. Bless you. Now, I can kind of forgive him for this. I mean, this is sometimes really useful and sometimes it doesn't do crap for you. But, I mean, Descartes came up with a Cartesian coordinate system, so he kind of bought himself a few of these. So what this says is, and this is a little bit weird. If I have a polynomial and, for example, this first one is kind of easy to see if I make it extreme. The extreme cases are easy to see. The little details in it are not as easy. This sort of relates to the upper bound there. What are the only possible values of x? What can you kind of characterize them as being to be roots of this, to be values that make this 0? What type of numbers do they have to be? They have to be negative, because everything up here is positive. The only way in hell it's going to become 0 is if it's a negative value I'm plugging in. So that all the other dudes here could have a chance to cancel out these guys, right? So really, it extends it. So this would say that there are 0 positive roots. 0 positive, let me be a little more specific. 0 positive real roots. You with me? Does that make sense? It's exactly the kind of thing we talked about with the upper lower bound. But we're going to expand on this. And this is actually Descartes' rule of signs, just to put it all out there. So what Descartes really says, 2 things. If the polynomial I'm looking at, let me see, how do I want to say this? Has n sign changes. Okay. So for example, this is an extreme case. There were 0 sign changes. Then p of x has at most n positive real roots. Now let me go even further. So that makes sense so far. This had 0 sign changes, so it had 0 positive real roots, right? But it goes even further. It could have, it says at most, doesn't it? Now, one reason I always want to hold off on this is, you guys have certainly talked about complex numbers. I'm not sure how you got here if you haven't, right? So you've talked about imaginary numbers, the I stuff, right? Can anybody tell me, where does that normally come from in a problem? Where do they normally kind of sprout from when I'm working a problem out? Okay, you know where I'm going. I like that. And so that comes from the quadratic formula, right? So normally when we do the quadratic formula, if the stuff under here is negative, that's going to come out imaginary, right? That's what imaginary numbers are square roots of negative numbers. So how many complex roots must there always be? They have to come in pairs, plus or minus. You guys semi with me? They have to come in pairs. Bless you. So really, what I can say is, if there's not n positive real roots, because this is at most, if there's not n of them, if not all of them are real roots, that means maybe one of them is complex, but that's not possible. Complex numbers have to come in pairs. So if there's not n positive real roots, the next number that there could be would be n minus 2. And if there's not n minus 2, it could be n minus 4. Down to 0. You guys look so happy about this. So let me give you, and again, remember, I think I might have made it clear that this guy is not always helpful. It almost is only helpful when it's an extreme. If you had this problem, let me make this 60. Let me make this 8. How big would your list be of possible real or rational roots? It would be big, right? It would be big. But the nice thing is, now that I know Descartes' rule of signs, my big-ass list is now cut in half, because there can't be any positive real roots. I'd only have to try the negative ones out. So Descartes' really useful in these extreme situations. With me? If it's not an extreme situation, it's like, well, it could have at most 8, but it might have 6. It might have none of them. Huh? That's like, okay, that's really nice. That's useful, right? Let's do a couple of specific examples of this. So if I had how many sign changes are there?
2.
So I see this is positive, so it changes sign here. There's 1. Where's the next place it changes sign? There's 2. 3. There's 3 sign changes, right? So how many positive real roots could there be? Or there could be 3. Careful. If it's not real, it must be complex, and they always have to show up in pairs. So the minute there's at least 1, there's 2. So if there's not 3 positive real roots, the next possible number would be 1. Because if there's not all 3 of them, that means 2 of them have to be complex. I see some of you guys look like you need some Tylenol right now. But I really want you to understand. Now watch this, watch this, watch this. What kind of answers would that have? Can you factor that? Good. No. Right? And if you look at the right part of the quadratic formula, what kind of answers will that have?
Negative.
Imaginary numbers, right? There'll be negative inside, so this is going to have imaginary. How many will there be? 2, because there's a plus or minus on there, right? You are never going to have an x minus I that you just solve. And that's never going to happen. They're always going to come from these quadratic that we can't factor. That's where quadratic formula is used, right? So if there aren't 3 real roots, if this is just a 2 there, I could have factored that. Then the other roots would have been, there would have been 3 real roots, right? If I put a 2 there, now this is just x plus 1, so there's 1, 2, 3 real roots. But the minute I do this evil thing, shit, now there's only 1 real root because the other 2 are freaking imaginary, right? So if there's not 3 real roots, the next possible one is 1 real root, because that would mean there's 2 that are not real. Okay, some of you guys that are a little less familiar with complex are like, oh, this is not real. You're making all this shit up right now. And yeah, I do that sometimes, but alright. Maybe. So see how this is a little bit useful, because then I know I'm guaranteed that one of my positive possibilities will work, but I don't know if it's actually rational or not. It might not come from my list. It's just got to be a real answer. I don't know if it's from my list. So see, that's why Descartes really doesn't help us in the middle. Now here's the other part of this. This might make some sense. If P of negative x has n sign changes, and that means the same thing, but this time just about negative real roots. You with me? Same exact idea here, except now this is going to be talking about negative. Then it would have n negative real roots, or n minus 2, or n minus 4, so forth. Right? So what about this guy? What's P of negative x? What's the shortcut for putting a negative x into something? All the even powers are going to have what happen? What's negative to an even power? Positive. So all the even power things are going to stay exactly the same. Do you guys see that shortcut? It's a really useful shortcut in general. So when I plug a negative x into x to the fourth, it's still going to be freaking x to the fourth, because a 4 just kills the negative sign, right? These guys, all the odd powers, are going to change sign. Because when I put negative x cubed, that's still negative times negative is now plus. So this guy stays the same sign. This guy changes sign. And of course the 7 doesn't care what the hell the x is doing. He's just negative 7. How many sign changes are there?
2. 1, 2.
So it's positive, still positive. There's one sign change, still negative, still there's one sign change. You guys see that? That's what I mean by sign change. It only changes sign from a term to the next once. So what does that mean about my negative real roots? How many could there be? 1. I like it. Okay, maybe. So if you had like a 10th power up here, maybe it would come out to be 10 positive real roots, or 8, or 6, or 4, or 2, or none. Right? Then you're like, that really doesn't tell me any damn thing. Okay, maybe. So I'm not going to make a huge deal, but the minute I say that, you still have to know how to apply this, but it very often doesn't help us as much. On the test, you can be sure I'm going to engineer something that this will actually help you on, so if you know it, you'll be that much better. If you don't know it, that's too bad. Okay, so let's go back to this guy. Now we have everything we need to do this problem here. So, have you guys got this first part? Did anybody look at that yet? What are my list of possible rational zeros? What's the nice thing about this polynomial? First number is a 1, yeah. So it's not going to have any fractional possibilities. So what does my list look like?
1, 2, 3.
Yeah, 1, 2, 4, 5. So now you can start pairing it up, right? 5 and 8 is 40, 4 and 10 is 40, 2 and 20 is 40, 1 and 40 is 40. So what really, really sucks is when you make your list and you leave somebody out and that happens to be an answer. So you don't want to do that. You want to make sure you get all the factors that exist. Now that's, how big of a list is that? 16 numbers, right? Because you got plus or minus. So there are 16 possible numbers to check out. So the first thing I talk about is B. Let me see. I don't think I made one there. This really helps. How many changes of sign are in the polynomial the way it is? Let's see. 1, 2. Exactly. So there's 2 changes of sign. So what does this mean? There's 2 changes of sign in the polynomial. What does it tell me? There's 2 or 0. Good. 2 or 0 positive real roots.
Why is it 0?
Because it always goes down by 2 until you get to 0. So the other ones went to 1 because the next one down will be -1, and that's freaky. Right? It's like you have -1 answer. I have less than no answer, right? Wait a minute. That's no good. So you stop at 1 or 0. Yeah. So what about p of negative x? What's p of negative x look like? Who's got that shortcut down? The only ones that are going to change sign would be which ones? Yeah, the odd roots. So that's going to be -x5. That's still the same. Plus 29x cubed. That's still the same. Minus 142x. And of course 40 doesn't care what's going on. He's just 40. How many sign changes are here? Yeah, 1, 2, 3. Good. So what does it mean? There's 3 sign changes. What does it tell me? 3 or 1 negative real root. So really, it depends on how much of a gambler you are. The odds are better that I have a negative answer, because there might be no positive ones, right? So when I start to do my synthetic division, I might pick the negative ones first, because there's a better chance I'm going to have one of those work. Does that make any sense?
Yeah.
All right, that's the only good thing. It improves my odds. So if you play any poker or whatever, that might interest you. Part C is where it's going to become a lot better. So it's divide by 8. Looking at the coefficients of my polynomial, I've got 1, 1. I didn't do it. Negative. So if I divide by positive 8, and I'm hoping this is, if you're not at the point where synthetic division is pretty quick, you need to get there very soon. I think once you see it done a few times, it's stupid quick. It's so much better than long. Unless you hit something. Yeah, this is just going to get big. Right? So here's what I do sometimes. What was it, 344? Sounds right.
Yeah.
Thank you. And then that's 309. And then that's 2472. And that's some big positive, big positive, big positive. I'm completely cool with that. As long as you don't do it down here. Big positive, big positive. No. Don't assume what I'm doing. Show me far enough. Does that make sense? I mean, that's going to be a stupid big number. Times positive is going to, and then added to positive. Who cares? I'm there. Where am I? What's there? Do you guys see that? That says big positive. Big positive. It doesn't say height spelled incorrectly. So what does it tell me? Good. 8 is an upper bound. More importantly, also, it tells me that 8. No? 8 is not a 0. I love it. So I can throw him out too, right? So there's no answers above 8, and 8 also doesn't work. So if you do negative 8, what do we get? As I've left myself the room to do it. Do negative 8. So 1 negative 8, negative 7, 56, 27. What the hell is that? 216. Negative 251. And then 16, 17, no, 2008? I don't know. Is that right?
Yeah.
Yeah.
And then 2150. And then big negative is going to be negative. So I've gotten where I need to be. You guys with me? So then what does that tell me? Negative 8 is lower bound. I like it. So negative 8 is lower bound. So what does so when I say this, update your list. Now, use everything you just saw and update it. My list was here, but now I can basically do what?
Yeah, right there.
Plus or minus 1, 2, 4, 5, and then I know that 8 and up and negative 8 and down don't work. So now from a list of 16, I went to a list of 8. That's decent, right? And if Descartes would have told me any damn thing, I might have taken that down to 4. Okay, I don't need to be bad-mouthing Descartes, by the way. He did a lot of stuff. So, and now, find all the zeros. So now you just have to start checking to see what works. Right? You just start with 1, try 4. It's kind of like, you might want to try a bigger number first, because if that works, what would happen to that last number if 4 worked? That would become 10. And if I still had some of my other crap in there, so I'm talking in general, it might be good to try a bigger number out, because then it's going to reduce that number at the end. Here, I've pretty much eliminated all my bigger numbers, really. So it doesn't really matter what you try first. Has anybody, while I've been talking so much, has anybody tried anything out and had it work yet?
Yeah, 2 works.
2 works. So if we look at that, 1, 1. So if we do that real quick. So all right so far? 2, 4, negative 25. 170, so that's, I feel like I've done something wrong if it works.
5 works as well.
Oh, I put a 1 there. That's a good job. Kept everything off at the beginning. 1 times 2 is 2. That's 3. 6. Negative 23. Negative, what is that? 46. 81. So that would be negative 162. And then I get, good, negative 20. Negative 40. 0. Cool. I like it. And real quick, I haven't really left myself a ton of room, and you might be able to tell that on this test, I'm going to probably bring some scrap paper, because if you don't hit the right one, I'm not going to end up with a list of like 20 long. 8 maybe at the most. So if it takes you a little while, you're going to need some room to put all your tries, right? I'm not going to leave you that much room on the test. What I've seen people do is they'll just start from here, and they'll try something else. Realize now my list would have changed, but it really is the same still, because all those are still factors of 20. You with me? Mm-hmm. So what's a good thing to try now? I think
5
somebody
works.
said 5 works. You guys see, you can just kind of keep going right off what you just got, put the next guess, and just keep going, so you can have a string of these synthetic divisions. Yeah.
And also, just does Descartes' rule of signs continue to carry up? So since we found 2 positive roots, would there be no more positive roots?
Yeah, there could be at most 2 positive real roots. I love it. So we found 2 positive real roots. So right there I could kill my list. I could cut down on my list. Right? So I would only try negative stuff going out. Cool. So right up here there's either 2 or no positive real roots. So the interesting is, the minute I found 1, I know there's got to be another one, but there's no guarantee it's a whole number.
Was it 2 or...
2 or 0. Right? So we found 2 positive real roots so far, which means I don't have to try any more positive candidates. There can only be 2 at most anyway. So now I can start trying negative numbers. Right? Well, I haven't even done 5 yet. Was that 85? Yeah. Sweet. So now let's start doing some negatives. And the minute you get down to quadratic, you can just try to factor that thing, right?
Right, you can do negative 4 now.
Negative 4? See if that works. So 1, negative 4, 4, negative 16, 1, negative 4, 0. I love it. So let's see. Can you guys help me out here? Where are we at? What could I write here as far as the factorization?
So x minus 2, x minus 5.
Good. X minus 5.
And x plus 4.
X plus 4.
And then...
And who's this guy?
X squared plus 4x plus 1.
Can you factor this guy? No. And in fact, will it have complex roots? So let me back up for a second. How many negative roots have we found so far?
No.
1, right? We found 1. And it could have been 3 or 1. So either this dude is going to give me complex answers, 2 complex answers, or it's going to give me 2 negative real answers. And of course they have to be negative, right? Because everything there is positive. They would have to be negative answers to make it work. So that's why this guy is 3 or 1. And actually I can see very quickly this is going to give me real answers, because b squared minus 4ac is positive. So how did I set up, do the quadratic for me here?
So, negative 1.
Yeah, negative b, so negative 4. Plus or minus?
The square root.
B squared, so 16.
1.
minus 4AC, I love it, divided by 2A. Sweet, you should all know that. Here's something else you should all know how to do. I don't want you to stop there, and I sure as all hell, please. This is a real quick way to make me cry. So if you want to make me cry, you know how to do it. If you do this, yay! All right, that kind of mistake should just not be happening now. Right? Why can I not do that? What's being divided by 2? Both of these, yeah. So how did that guy escape it? So if you put him over 2, you're a little better, right? What's even better than that is to take a second first and do what with the radical 12?
Rationalize it.
Don't rationalize it, but simplify it, right? I call it reducing the root. Do the part you can do. So 12 has got 4, 3 in it, right? Square root of 4 is 2, and you got a 3 left inside. And now you could wish that Jeff could use space better. But also you could do negative 4 divided by 2, 2 divided by 2, and you get that. Sorry. Alright, so now you can do negative 4 divided by 2 is negative 2. 2 divided by 2 is 1, and there you go. As long as you divide both of them by it, you're fine. That's legal. It's only when you do something like that that's not good. And both of these answers are real, and they are negative. So then I was in this situation there. 3 negative real roots and 2 positive real roots. Okay, cool. So that's exactly the kind of work that you need to do in section 3.4. And you see, section 3.5 is all about complex numbers. And most of you guys should have already seen it. I already saw a few people give me a pained face. So I don't know if you've had bad experiences with complex numbers in the past. But real quick, the funny thing about section 3.6 is it is section 3.4 including complex numbers. So 3.6 actually has very, very little new. And the new thing is something we already know, hopefully. So help me out real quick. If I had this one we had earlier. Quadratic formula would say, right, negative b, and then b squared minus 4ac all over twice a. So I get negative 1 plus or minus radical negative 3. And what's a slightly better way to write radical negative 3? I radical 3, right? You with me? Can't dig the 3 out also. It's still radical of it. This still says radical negative 1, radical 3. That's what that is. But I've just replaced radical negative 1 with I. Okay. Can anybody tell me the relationship between the two? Here's one complex number, and here's the other complex number involved in this answer, right? What's their relationship? I love that question. You're all like, I don't know them really. But, I mean, what's the name for if you have a complex number like this and you do the only change that this has in it?
Complex conjugate?
They're conjugates of each other. Good. Complex conjugates of each other. I like it. And we had that earlier when we did like radical 2 minus radical 3. We had to multiply by radical 2 plus radical 3. That's the conjugate. This, amazingly enough, is called the complex conjugate because it's complex. But you'll always have, if there are any complex answers to a polynomial equation, they have to show up in conjugate pairs. Because where the hell would they come from? From here. Right? That's always going to end up with plus or minus this conjugate pair stuff. Cool. Okay, maybe. So what I do right now is I just want to talk a few things about complex numbers. And if there's anything that you've never really understood or something, we'll bring it up now as I talk about it. Otherwise, I'm going to go kind of a little quickly through it. First off, what the heck is a... What's the difference between complex number and imaginary number? Does anybody know? I know you know. Hold on to it.
Complex number is like 2i plus something like plus a number.
I like it. So a complex number is specifically a real part plus an imaginary part. Right. Where, of course, this would be the imaginary number, the imaginary part, and it's the real part. So real and imaginary together are complex. Now, of course, every single number you've ever seen, like 7, is a complex number that just happens to have b with a value of 0. If it was 1, it would have an I in there, right? So this is like 7 plus no I. It's kind of evil. It's got no I. So that's the real basics. That's the form of a complex number. And the really beautiful thing is some of the basic... whenever you learn new numbers, which doesn't happen very often, you learn the operations you can do with them. So you can add them, subtract them, multiply them, divide them, right? So of course, adding, subtracting is stupid nice, because in this case, no, adding, subtracting. Let's make that. What does the I act like, really, in this case?
It's just like an X.
It's like an X. It's like a variable, right? So that's nothing new. The only thing you have to be careful about, of course, is bringing the negative through. Don't make a mistake like that. So you get 7 minus 4. Negative 3i plus 2i minus I. Right? Okay. So that's easy. Adding, subtracting complex numbers, easy. Multiplying complex numbers. And really, before we get there, there's a little side note. Here's something you should all know already. But we're going to go over it. So I is really defined to be the square root of negative 1. That's what I is. That's what I do be. It's not just people playing around with numbers and saying, I don't know the square root of negative, let's give it a variable name because I don't know what the hell. No, it goes beyond that. You can't have electromagnetic theory without this. You can't have describing how the voltages go through your lines to get to your house. You can't have that. It requires that. In fact, you guys know, let me see you guys, a little physics for you. When you have a magnetic field, you very often have an electric field with it also. So whenever you have a current flowing through a line, it actually sets up a magnetic field. Did you know that? No, you didn't. And so when I describe that field, and when it goes, it's like a sine wave very often. When it do that, it's got an electric field part and a magnetic field part. When you look at the equation, the electric field part is the real part. The magnetic field part would be the imaginary part. So if I didn't have imaginary numbers, there would be no way to capture the magnetic part of things, and that would so suck, believe it or not. So, I mean, there are uses to this. It's not just making something up, and that's why we call it imaginary and all that kind of crap. In engineering, you use a J for complex numbers, because they have to be different. So what does this lead to, though? What is I squared? All right, good. So all you guys are like waiting for me to get there. Please just say it. So what's I cubed?
1.
Careful. Oh, she overstepped it. So I cubed would be I squared times I, right? That's I cubed. And what's I squared? So I cubed is negative I. You guys semi with me? And what's I4? Yeah, because I4 would be I squared times I squared. That's negative 1 times negative 1 is 1. So then I5 would be I5 would be I4 times I. I4 is 1, so I5 is I. It starts over again. I6, I7, I8. Bam, man. It just keeps going forever. Real quick, though. I mean, watch why this makes sense. What's 1 to any damn power? 1. So 1 to the 1 squared, 1 cubed. With me? What's negative 1 to the first power? And then negative 1 squared. And then negative 1 cubed. Do you see how it's got more variation, obviously? This is no variation. This has every 2. And this is basically like a 1. Square root of 1 is 1. You with me? So it should have maybe some of this kind of alternation, this cyclical pattern where it comes back on itself. But it takes it 4 goes before it starts over again. And I'll bet you right now, some of you guys just start hearing, what has just happened? But you guys with me on this? Just the basic 4. So if I wanted to know what I to the 8th was, well, that's just I to the 4th squared, right? 1 squared is 1. So any factor, anything that 4 goes into, any power of I that 4 goes into, that's going to be 1. And here's the really kick-ass thing. In general, if I had I to the 47, 4 goes into 47 how many times? 11. With how many left over? 3. So this is basically equal to I cubed. It's going to be equal to I to the remainder when you divide by 4. Because every 4th one is going to go here. Then this will be the 5th one, remainder 1. 6th one, remainder 2. 7th one, remainder 3. 8th one, no remainder. Goes in immediately. It's 1. Right? So I could do that stupid thing until I finally get up to 47, or I can just go, wait a minute, there's a freaking shortcut in there. The remainder tells me where I am in this cycle. Alright, now compared to knowing this is nowhere near as important. But you know I'm going to have a question like that on there, so you should still know it. But this is the most important stupid thing in this list. For several reasons. I've got a number that I square and get a negative number. Holy shit. Right? And I should expect weird things to happen with this because it was weird to begin with. But that actually opens a lot of doors for us. Let me do a little side note. How do you factor this? And that kind of relates to the fact that when this is equal to 0, it's got 2 answers, 2 and negative 2, right? Would this have any answers, this equal to 0? Would that have any answers? No real answers. But it has to have 2 answers. There has to be this many answers to any polynomial equation, the highest degree I see. And that just so happens, how do you factor this stupid thing? It's not x plus 2, x plus 2, that's for damn sure. They have to be different signs.
X plus 2i, x minus 2i.
Exactly. That's what saves our ass. Because now, work this out. What do you get? X squared minus 2ix plus 2ix, so that cancels. And then you get minus 4i squared. But what's I squared? Yeah, I squared is negative 1, so you get x squared plus 4. So that is how you factor a sum of squares, which you've never been able to do until this class. You just have to do it over the complex numbers. Those are the only things that will square and come out negative, right? That's why this makes it, because now I can say, how do I solve this? Take the square root, of course, and then you can see it more directly. What's the square root of negative 4? 2i, 11. Okay. Way early, damn. Very dedicated to his class, I like that. Alright, so that was a little side note. Now let's come back to how do you multiply complex numbers? Well, we just did basically in one example. The first step is treat I like a variable. The next step would be wait, I is not a variable. It's a value, and maybe I can simplify it. All right? So first you just FOIL it like you always would. Then, oh, you're going to do it alone, Jeff. All right, I'll do it. 15I minus 21 I squared. Cool. Now normally the only thing you can really do would be to put these together in the middle, but we know what I squared is. Negative 1. So now I get 10 plus I plus 21, so I get 31 plus I. And the reason this makes ultimate sense is because when I multiply two complex numbers, the answer better be a complex number. I better be able to put it in the form of a complex number than A plus BI. If it's not in that form, I haven't gotten it all the way done yet. So that helps us when we go to divide. I divide two of these weird things.
Do you multiply by the conjugate?
Yeah, I love it. See? You had your hand up there, you were right.
I was going to ask a question. Are you going to have a problem on the test with the multiplication where you're going to have 31 plus I and you have to get it back out to 2 plus 3I?
Oh, no. Because it's sort of like, that would be a neat problem, but not at this level. Because, I mean, if I said factor 28, there's a few different ways to do it, right? So factor 31 plus I, there's a few different ways to do it, and it's really difficult to figure out what would work. Do you kind of follow? Yeah. And then, we'll stop there. Yeah, there's a but you're right. I would just multiply by the conjugate. Right? Because that's how we handle radicals in the bottom. We multiply by the conjugate. That's all I is a radical of a negative number, but we can't get past that. So on the top, you get almost what we got here, except there's a plus. It's too bad for us. So we get 10 plus 15 plus 14 plus 29i. Plus 21i squared, but I squared is negative 1, so you get minus 21. Is that cool? What do you get on the bottom? Bottom's a little easier because the middle terms, I've designed it so that they will
5 minus 14 squared.
cancel, right? So you get 25 minus 35 plus 39. Those cancel. Minus 49i squared, which is plus 49. I love it. So the bottom now is completely real. So when you multiply by the conjugate, when you have radicals, that's called rationalization because you made it rational. This could be called realization because you make the bottom real, right? But they just don't call it that too bad. So on the top I get negative 11 plus 29i. On the bottom I get 74. Cool. Cool. Is that good? This should be mostly reviewed. Yeah, you can go one more step to put it in this form.
Well, I was thinking, like, could you square the top and bottom and from that take away the I?
If you square the top and bottom, number one, that's illegal. So that's kind of a big one. But secondly, you wouldn't kill the I because it would just get picked up in your foiling. It'd still be there,
Okay.
right? Yeah.
So on a test, would you take a point off if we left it that way?
No, it's all right. I just want you to realize what I was saying earlier. When I multiply two complexes, it better end up a complex number. When I divide two complex numbers, it better end up A plus BI. But if you stop here, I'm not going to... That'd be a little petty. And I'm not that way yet. Believe it or not. Okay. So that's section 3.5. There's really nothing more going on in there. Cool. So we're done early. That's as far as I want to get. Don't forget the quiz on Monday. 2-7 up to 3-3.
What is that?